All right. Couple of announcements. I guess all of you know that the exam is on Monday, coming Monday, 7 to 9. And the TAs will post the room assignment. It's the same as last midterm, more or less, by the end of this week. And the review session is from 5 to 6:30 on Friday. So they will tape it if you cannot come, but the review session is 5 to 6:30 on Friday. Okay, so I posted the syllabus. It doesn't include this week's material, including today's lecture and Thursday's lecture. Okay, it's only till last week. And it also doesn't include Turing machines, which we did after automata theory, right? Turing machines will be only on the final. So only the algorithm stuff on recursion, dynamic programming, and graph algorithms. Okay, so today is about greedy algorithms. What are greedy algorithms, right? We'll see a lot of examples because there is no good definition of what a greedy algorithm is. Okay, we kind of say, we know it when we see it, kind of definition, right? But they are very people don't agree on what algorithms are greedy algorithms. For example, some people classify Dijkstra's algorithm as a greedy algorithm, and I strongly disagree, right? It's not like the other people don't have a valid opinion or I don't have a valid opinion. It's just different perspective, okay? So, roughly what characterizes an algorithm being I just said it, no? It's 2 minutes ago that this week's lectures are not going to be on the midterm. Okay, I started the lecture with the announcement. Okay, all right. So what's a greedy algorithm, right? Greedy algorithms are characterized by, they're kind of simple algorithms that make decisions in an incremental fashion, one step at a time, without backtracking. Okay, so what does it mean, right? So it's not but it's just an English description, right? And decisions are very simple, made based on some simple rules, usually some priority rules, and that's really a vague definition of a greedy algorithm, right? It's not very precise. What are the advantages of greedy algorithms, right? Well, they tend to be simple, right? Greedy algorithms tend to be very simple. Because they're simple, they're easy to implement, they're going to be fast in practice because they're simple. And well, if the ease and simplicity was the only reason and they didn't work, we wouldn't be discussing it in an algorithms class, right? So there are some nice examples, many actually, of examples where greedy algorithms do work to give the right answer. Okay. So obviously, if there are simple, nice algorithms which give the right answer, why shouldn't we be interested in them? We should be interested, right? And even when they don't give the right answer, they often, in practice, in some cases, not always, maybe you're implementing some complex system and you don't have time to think of a proper algorithm, or you don't have the expertise, and people come up with simple greedy algorithms as a first cut till they maybe ask an expert or have time to refine the algorithm or something. So they're first cut heuristics in some cases, even sometimes when problem is not well understood. Okay. So what are the disadvantages of greedy algorithms? Because everybody can design a greedy algorithm. Okay. You don't need to take an algorithms class to design a greedy algorithm, right? The first thing that comes to mind usually is a greedy algorithm. Okay. So it cannot be that all these clever problems can be solved by the first thing that comes to mind without any training, right? So there must be that's one disadvantage, right? That so they look plausible for many problems, and they don't work many times. So that's one of the reasons greedy algorithms are not good from a formal point of view. That they don't often work. And it's easy to confuse oneself into thinking that they work, so it's dangerous from a formal point of view. And the other thing is that it's not a priori clear, because for a given problem there are many different types of greedy algorithms that suggest themselves, and how do you choose between them? And that's also non-trivial. What's a systematic way of figuring out which greedy algorithm is the right one? And we'll see some examples of that, okay? Okay, so since this is a course where one of the main things we are trying to teach people is to be more rigorous in their thinking about correctness and design, and greedy algorithms are the example of something which is can be like misleading in many cases. You know, there's more of a burden when you think of a greedy algorithm to prove the correctness. Even more so than, say, for example, when you do recursion, you have some sense of the recursion. And for example, if you do DP, the recursive definition, it's easy to check whether it's correct or not, because you follow the proof by induction. You know, if it's a high level, it's easy to check. With greedy algorithms, it's very often not easy to check, so a proof is very important. So our policy, I mean, not in exams, but if you write an algorithm, a greedy algorithm in 374, you should write a proof on the home. Okay, all right. And again, greedy algorithms come in two flavors: non-adaptive and adaptive. Non-adaptive algorithms sort of fix the decisions a priori and stick with that order. Adaptive, they make decisions adaptively, and we'll see examples of both. It's not so important to distinguish these two. So the idea for the rest of the lecture is to see several examples where greedy algorithms work and pick up some proof techniques. Even when people are intuitively clear on why things work, sometimes it's a vocabulary issue of how to phrase it in a way that is mathematically sound, and you're kind of convinced that it is correct, right? So we'll pick up some proof techniques. Okay, so let's go to examples, right? Some problems. Okay, here is a very simple problem. I have some n jobs that I want to schedule, and the jobs have lengths or processing times. Okay, so I have 6 jobs here. Job 1 has size 3 or processing time 3. This job has size 4. This job has size 1, 8, 2, and 6. Okay, what's my goal? My goal is to schedule them on one machine or one processor or give it to one person, right? Okay, you want to sequence the jobs in some order. That's a schedule, right? Typically when you say schedule, you know, which order do you want to do them? And scheduling has many objectives. So in this problem, the objective is to minimize the total waiting time or the average waiting time. Okay, so what is the waiting time of a job? It's when it is finished, basically, or you can think of it as the finish time minus its processing time. When it starts also, it's the same as that. So the waiting time of a job is when it finishes. Okay, you can alternatively think of it as minimize the total finish time of the jobs. Okay, is it okay? Okay, so let's see. Example schedule. Suppose we order in the same order as this numbering. Okay, what is the total waiting time or total finish time? Well, the first guy finishes at time 3, right? Because he starts first and finishes at time 3. When does the second guy finish? At 7, right? Because he has to wait for this guy and then it's processing time 7. Or is the next guy, he has to wait for these two to finish, right? 3 plus 4 plus 1. That's what we are trying to minimize. Okay? Okay, what should we do? What is the right schedule for this? What is the schedule which minimizes the total waiting time? Sorry? Yeah, which job should we do first, right? Yeah, intuitively, it is the shortest job first, right? You know, you should put the small jobs first, right? Okay? Yeah? Okay. But how do we prove it? Right? That's optimal. Yeah. Okay. So optimal schedule is to do the shortest job first. So here there are no ties. So without loss of generality mechanism, there are no ties. So you should do job 1 first, and then job 3 first, then job 5, and job 1, and so on. Right? Okay. If you calculate, you'll get some smaller answer than this, the total waiting time. Is that intuitively okay? It means, okay, how do we prove it? Well, why do you believe it then, if you don't, right? I mean, you have some sense of why that's true, right? Yeah. Yeah, okay, yeah. So, I mean, it is, I get that all of you have good intuition on that. I'm not trying to minimize that, right? So the part of the thing, yeah. Okay, inductive proof on the number of jobs, okay. Okay, let's stop there, okay. How do we do the induction? That's, yes. I want us to do the induction with 3 jobs. How will you do it? Not quite. How would you consider it as one job coming after, right? It's not as, because you have to count them separately, right? Right. Okay. No, induction is a good idea. The question is, to get to the induction, so what do you want to kind of prove, right? If you want to use induction, you want to kind of prove that the first job should be the shortest job, right? It is not completely obvious how to do that, right? So to formalize that takes a little bit of work. Yeah, so let's think about the ideas, right? What about proof by contradiction? So, right? So what I'm trying to say is, induction is a little hard because how do we understand what the optimal schedule is, right? Yeah. Okay, so that's a better idea in a certain sense, that he's saying, let's start with the shortest job first and then say if you reverse anything, you'll get a better thing. But maybe there's some other schedule which is actually reversing a lot of things, a lot of steps, and then it's better, right? But let's flip that argument around and say, okay, if there is a schedule which is optimal and it is not the shortest job first, can we improve it by swapping? Okay. All right. So the intuition of 2 jobs is good, right? If you have 2 jobs, how would you argue? If you have 2 jobs, you have to first argue. How do you argue that 2 jobs you have to do the shorter one first? You have to do this math, right? Okay. You have to do the math. There is no choice there. Okay. If you can't convince yourself of 2 jobs, you are not going to be convincing yourself about many jobs, okay? So the good thing about induction is, yes, first we have to argue why for 2 jobs doing the shorter one is better, right? So for that you have to do the algebra, right? And like what you said, you can count, right? For 2 jobs you can say there are only 2 schedules, and you can do the algebra and you see that, it is better to do the shorter one first, okay? Okay, now like when we want to argue for a arbitrary instance, we can look for an arbitrary schedule which is optimal, and if it is not shortest job first, what should happen? That means I have an optimum schedule in which the ordering is not shortest job first, right? Okay, so okay, to make it formal, I want to prove this to you. This is what is called an exchange argument, okay? You're intuitively seeing it, but let's formalize this exchange argument, right? Okay. It's all about converting intuition into a formal argument, and it's a skill. It is not it's not something that is difficult in an intuitive sense, but it's a skill to develop to do it formally. Okay. So let's assume we sort the jobs so that the processing times are increasing. Right, 1 to n. We shuffle the jobs so that processing times are P1 to Pn. And we believe that, you can make it strict if you want. And we believe that this is the optimum schedule, right? J1, J2, Jn is the optimum schedule, right? Because we sorted them. Okay. Okay. So let's say that, there is some other schedule which is optimum, which we don't know, right? Okay. So we'll say that, a schedule has an inversion if the 2 jobs A and B such that A is scheduled before B, but the processing time of A is bigger than processing time of B. Okay? Yeah, we schedule a bigger job before a smaller job. Okay, then we have a schedule has an inversion. Okay, we believe there should be no inversions in the schedule, right? That should be the outcome. Okay. Okay, then here a small claim. If a schedule has an inversion, then there must be inversion between two adjacent jobs. Okay, what is it saying? If my sequence of the numbers is not sorted, then there must be two guys who are next to each other who are not in the sorted order. Does that make sense? Everybody agrees with that? Yeah? That if I schedule a smaller job later than a bigger job in a schedule, then I can find two adjacent jobs which are in the wrong order. Yeah? Will you agree with that? Yeah? I don't have to prove that, right? Okay? Okay, you can prove that yourself. Okay? Okay, so I mean, this is important because what we can do is that we can swap those two and improve the schedule, no? Yeah? Okay. Okay, so more formally, if there is, recall that the shortest job order is J1, J2, Jn because we sorted the jobs. Suppose there is a schedule which is optimum, right, which is not the shortest job first. So the way to argue that is look at an optimum schedule with the fewest number of inversions. There must exist some optimum schedule, right? So among all optimum schedules, pick the one with the fewest number of inversions. Okay? If there are no inversions in that, what does an inversion mean? An inversion is a pair of jobs such that the smaller job is after a bigger job. Right? If there are no inversions, what is that schedule? It's the shortest job first, right? And we are done. Okay? If the optimum schedule with the smallest number of inversions has at least one inversion, then it must have two jobs which are right next to each other such that the smaller job is coming after the bigger job. Okay? What can we do then? We can swap them, right? Yeah? What happens if we swap them? We will get a better schedule, no? Yeah? So then, we swap them and then we'll get a better schedule, and they'll contradict the fact that we chose an optimum schedule. Okay? Okay, so this is a long story to say the following. How do you argue that the shortest job first schedule is optimum? Suppose there's an optimum schedule which is not the shortest job first. It must mean that there are two jobs which are right next to each other such that the smaller job is after the bigger job. So what do? We just swap those two. So what is the advantage of swapping just those two? We don't have to disturb the rest of the jobs, right? Yeah? Otherwise, how do we know if this one small guy is here and small guy is later than the big guy and we try to move them, there are other jobs which have to shuffle, right? That's hard to argue. But if you have two jobs which are right next to each other where the bigger guy is coming before the smaller guy, we can swap them. Nothing changes for the rest of the jobs. And for these two jobs, we get an improvement because we already understand the two job case, right? And this proves that, if you cannot have this inversion in an optimum schedule, okay? So effectively, we have reduced the argument to two job case, right? Using what's called the exchange argument. We're just using swap, right? Okay. So it's not so easy to do induction directly because we may have to move things across, right? But arguing about two guys which are locally next to each other is easier without touching anything. Okay. So the intuition is correct, but formalizing it requires a little bit more work. Okay. Is the proof okay? Yeah? Questions about the proof? Yeah? All right? Yeah. Well, we have already spent some time discussing the problem. So, it's a job scheduling problem where we are trying to schedule the jobs in a sequence to minimize the total waiting time. There is no data structure here. So it is just an algorithmic problem. We are not really thinking about data structure. To schedule the jobs, you just sort the jobs in the increasing order and schedule them in that order. Yeah? Okay? All right? Any questions on the proof technique? Okay. Here is a slight generalization. I thought I had it on the slides. Every job now, in addition to having a processing time, has a weight, which is its importance. Okay, and you want to minimize the total weighted completion time now. Okay, so let me check why I didn't have it here. Let me see. Something is off. Okay. Okay. So this is just, I'll just say it in words. If every job has a weight, say some jobs have weight 10, some jobs have weight 1, and so you can have the case that a big job has huge weight, so you can't ignore it, right? Even though, see, right now, why did we schedule the short jobs first? Because they're all equally important, right? So doing the short job is the same value as doing a big job, right? But suppose I put weights on the jobs where each job has a different weight. One job has weight 1, one job has weight 100, or another job has weight 35, and now I want to minimize the weighted sum of the completion time. So my goal is that if this job 5 finishes at time 20, you have to weight it by its weight, right? So you multiply it by the weight, and that's what you want to minimize, the sum of that. Okay. In that case, you can argue that the right greedy algorithm is to look according to the weight divided by the processing time. Okay. Instead of shortest job first, you divide the weight divided by the processing time and sort according to that, and the same exchange argument will work. Okay. So try to play with that. Okay. So here is another similar job scheduling problem, but objective is different. Okay. So again, I have a bunch of jobs. Each of them has a processing time. I have one processor, but now jobs have deadlines. Okay, there's no time, waiting time. Jobs have deadlines. I want to finish this job by deadline 6, this job by deadline 8, this job by deadline 9, and so on. Okay. Okay. Sounds good? Yeah. Okay. Now, what's my objective? I want to schedule them to minimize what? Maximum lateness. Okay. Ideally, I would like to schedule them to finish them all before their deadline, right? Yeah. But maybe I won't be able to finish all of them by the deadline, in which case I want to minimize the maximum lateness that I incur on any job. So if I do this schedule, for example, J3, J2, J6, J1, J5, J4, you can see when they finish, right? Because J3 is a size 1, it finishes at time 1, this finishes at time 3, this finishes at time 5. Okay, all these guys finish on time, except, look at J1. When does J1 finish? Time 8, but J1's deadline is 6, so it's late by 2 units, right? And J5 is fine. J4 is finishing at 15, but its deadline is 9, and the lateness of this job is 6. And we want to minimize the maximum lateness, so the lateness of the schedule is 6, because that's the maximum for all jobs, right? Yeah, because it's defined as the maximum or all the jobs of their lateness of that job. Does that make sense? Yeah. What the objective is? Yeah. Okay. How would you solve this problem? Yeah. Earliest deadline first. Okay. He wants to do earliest deadline first, right? So, I mean, if you want to do, there are many possibilities, right? If you're thinking of a greedy algorithm, right? He suggested earliest deadline first, right? Sort according to the deadline. But these two are also natural, right? You can say, okay, look, look at the job with the least slack. Look at the job with the smallest completion. Does this make sense? Shortest job first. All of this, that's the problem with greedy algorithms, okay? That there is no clear guideline on why certain approach should work or not work, okay? All right? But why did you say earliest deadline first? Because you knew it already, or okay, is it intuitive, earliest deadline first? Yeah? Why is it intuitive? So it is correct. This gives you the right algorithm, okay? Okay, so let's find, okay, but this is not how we discover algorithms, right? You may think that this will work first. Do you think this works first? I mean, do you think this works? So the important skill in algorithm design, part of it is to find counterexamples. So I claim that shortest job first won't work. Why? How do you convince me that doesn't work first? Yeah, so the intuition is correct, right? That you can't, the deadline has no connection with the job length, right? Maybe, I have a job length of size 1, but its deadline is like infinity. It doesn't matter when I do it. But then there's a job of length 2, but its deadline is 2. If you don't start it right away, you'll miss the deadline, right? So you shouldn't schedule the shorter job before. So that's easy to connect. What about the second one, though? That seems more plausible, right? Can you find a counterexample to the second rule that it won't give you the right schedule? Shortest slack first. I ask you, give me a counterexample. What does it mean to give a counterexample? That means that you have to come up with an example for which this algorithm will give you the wrong answer, right? Yeah? So why is this a bad thing to do? Or can you think of an intuition for why that's not the right thing to do? It seems like it's plausible, right? Yeah. Yeah. Okay. Yeah. So we have to do some algebra, right? Yeah, so that makes sense, right? So what he's saying is that, look, what if I had, this doesn't distinguish the size of the job at all, right? So I could have a job with of size 1, right? And deadline equals to 2, and a job with size 100, right? And deadline equals 101, right? Yeah. So what should we do? Schedule first? Okay, but in this case, yeah, makes sense. Yeah. Okay. If you schedule the 100 size job first, we'll make the job with smaller job wait too long, right? Okay. Yeah. Agreed. Okay. So now the question is, the third rule, the earliest deadline first is completely ignoring the size of the job, right? So that also seems implausible, no? Yeah? Okay, but it turns out that's the right algorithm. So how do you figure it out? Well, there is no good way to figure it out other than trying to prove that it is correct, and coming up with either a counter example like we did, or figuring out that, actually it is doing something right. Okay? All right. So one way to think about this is as follows, right? So we will again use an exchange argument. Okay. If you believe that the earliest deadline first is correct schedule, right? we will try to use an exchange argument. For 2 jobs, you have to figure out what is the right answer. Okay? So again, or think about it inductively. If you had 2 jobs, how will you schedule? Which one would you schedule first? Yeah, I mean, so that's the thing. You have to, would you prefer? I mean, it boils down to understanding the 2 job case. For 2 jobs, what is the right way to order them? Right? I claim it's always better to schedule the one with the earliest deadline first. Right? Why? So let's look at that, right? Okay. So okay. Okay. So I claim. Okay. So let's see. If I have 2 jobs, what will you do? This one has size A and B, right? And this one has D1 deadline and this one has D2 deadline. Okay. So there are some jobs which are scheduled here and some jobs which are scheduled here, right? If I swap A and, if D1 is greater than D2, I claim that swapping A and B doesn't make anything worse. Okay. So what is the lateness of this guy? Okay, let's assume they're both scheduled before their deadline. Let's say both are scheduled before deadline. Then what happens to their lateness? Their lateness is 0, right? If I swap them, will they still stay within their deadlines? Because if D1 is bigger than D2, swapping them doesn't make it worse, right? Okay. But if D1 was bigger than, okay. So what I'm trying to claim is the following. If I have 2 jobs which are right next to each other, yeah, and this guy's deadline is bigger than that guy's deadline, I should swap them and the maximum lateness will not worsen. It will only improve. Okay. So for 2 jobs, putting the guy with the larger deadline second is always better in terms of the objective, which is the maximum lateness. Is that, that's a claim I'm making. If I have 2 jobs with different deadlines right next to each other, putting the job with the later deadline second is always better for the maximum lateness objective. Yeah? Does that make sense? Because, this guy's deadline is smaller than this guy. Why would I put him here with the lateness, right? Because I'm measuring the max of the 2. Okay? So for 2 jobs, it's always better to schedule the earlier deadline first. So in general, if you have a big schedule, you should always swap, right? If the 2 guys with deadlines in the wrong order, you should swap and it will improve your objective. So I can keep on swapping till what happens? Earliest deadline first is your schedule, right? So same proof, right? So this is also an exchange argument, right? So if you can convince yourself that this is the right thing to do for 2 jobs, then you have an intuition for doing it for a larger number of jobs. All right? Okay? So that's how so there is no good rule. When you first start thinking about the problem, there are many ideas that come to your mind. The way you prune out those ideas is either by coming up with a counterexample or coming up with a proof by playing with small number of situations and getting the intuition of what makes sense. Okay? All right? So the same argument, except that the same exchange argument will give by considering 2 jobs and swapping them. All right. Okay. So those 2 are one kind of greedy algorithm where you feel that, oh, there's an intuition for small number of jobs. You look at a bigger sequence of jobs and then you do an exchange argument to argue that the right order is given by some simple rule. Okay. Yeah. Yeah, shortest job first. Yeah. Okay. So here is a exchange argument again, but in a very different situation. So this is a different kind of problem, right? Not jobs right now. So it's such a simple problem that you'd have a hard time understanding why this is interesting, but we'll see why it's interesting. So I give you a bunch of items, right? E1, E2, E6, 6 items, and all of them have some given weight. This guy has weight 3, this guy has weight 2, 1, 4, 3, 2. And I also give an integer k, and I want you to pick the largest k guys. Okay, so that's completely trivial problem, right? You would say, okay, what will you do if I want to say, I can only pick 2 items. Which 2 items should I pick to maximize my total weight or total profit? You would pick 4 and 3, right? All right. If I give you 3, what would you do? If I allow you to pick 3, you would say, okay, 4, 3, 3, right? Yeah? Okay. So this is completely easy, right? There is nothing to it, right? So, if you look at the greedy algorithm, it looks very simple, right? In this case, you say, okay, you start out the empty set, while the set is less than k, pick the one with the largest weight among the remaining items, add it to your set, and keep on doing it. Okay, let me make it a little bit more interesting. I now give you, I changed the slides, but didn't get, okay, it's a little bit more interesting. So I have again items, but these items are grouped into different sets. So these 3 are N1, these 2 are N2, and these 2 are N3. And now I say, okay, you can pick 5 items, but you can only pick 2 from this group, 2 from this group, and 2 from this group. Okay? So what would your algorithm be? Okay, so what is the group with the biggest one here? Okay, so then what? Okay, what is the next biggest one? Okay, here or here? Mm-hmm. Yeah, okay. So, okay.
So essentially, see which group got the biggest one, all your cases.
Mm-hmm. Yeah. So this works. Do you see the algorithm? What is the algorithm here? Can you formalize it? Yeah. In a proper. So is the algorithm completely clear here? Yeah. No. So okay. So what would you do? If see the general problem is that I have many groups. Each group has its own budget, right? Yeah. And there's a total budget also. What is the natural greedy algorithm here? Yeah. What? Yeah. Why? So what I claim is a simple greedy algorithm. You pick an item with the largest weight, as long as what? What is the first item you pick? The largest weight item. Okay, but what about the next item? Okay, but you may remember this could be smaller than you may exhaust this also, right? If k was 1, what will happen here? You're already done, right? Okay. So here is a simple greedy algorithm for this scenario which is a very generic greedy algorithm. You start out with the empty set. What is the first item you pick? You pick the item with the largest weight that is still possible to add to the ones you already picked, according to the constraints given to you by the system, right? Okay. So what are the constraints? The constraints are that you cannot take more than 5 items here, k, and in each group you cannot take more than its budget, right? So what is a nice greedy algorithm here, which is a generic template? You pick the item which has the largest weight among all the items which can be added to your current set without violating the constraints. That's a lot of words, okay? Okay, what are the constraints? What is X? X is a set of items that we already picked. X is satisfying the constraints. What constraints is it satisfying? The total number of items in X is at most K, right? And in each group, X has picked only the right number, no more than what the budget of that group is, right? Which item should I pick? Among all items that I can add to X without violating the constraints, you pick the one with the heaviest weight. Does it make sense? Or no? The algorithm does make sense? Say, choose among all the items. Say n prime is the set of all the items which are remain such that if I add it to my X, I will not violate any constraints. Those are all feasible items that I can add. Among those, pick the one with the largest weight. That's a simple greedy algorithm, no? Yeah, the natural greedy algorithm. We're not making, you pick the first item without thinking, right? The best item. Then you pick the next item you can add to the current set without violating constraints and keep adding till you stop, right? That works. You can prove by, easily that this will work. So, I claim that this is a generalization of the previous one, which is very simple. Now, how do you prove that this one is correct? Can you argue that this one is correct? Yeah? How will you argue that this one is correct? Again, you can use an exchange argument, okay? Okay. How do you prove that this simple algorithm is correct, by the way? Picking the K largest ones is correct. They may be ties, right? You may have two guys with the same weight, and maybe you pick this guy instead of that guy. So how do you argue that you have the right solution? So if I have K equal to 2, maybe you picked 4 and 3 while I picked 4 and 3. How do you argue that my solution is not any better than the other one? You can swap, right? Right? You can take an optimum solution, and if it is not your solution, you can swap and argue that your weight is no worse than the optimum solution's weight, right? So you have to do the same thing for this more general thing. This is a little trickier, but I want to claim that when we see minimum spanning tree and maximum spanning tree, we are going to use the same algorithm. You have seen Kruskal's algorithm, right? You have seen Kruskal's algorithm for minimum spanning tree? Okay, have you seen Kruskal's algorithm for maximum weight spanning tree? Probably not, right? Solving minimum weight spanning tree is the same as solving the maximum weight spanning tree. Why? Because you can flip the weights of the edges. You can negate the weights of the edges, okay? And that algorithm is also a greedy algorithm, and the reason why greedy algorithm works in all these simple scenarios is because there's an underlying structure called a matroid, okay? This is just to give you some, if you're interested, this is a way to beyond the class, but there is a notion of these constraints called matroids, and the reason why they're called matroids is because they are the same phenomenon as matrices. You all learned linear algebra, right? How do you find a basis of a set of vectors? How do you find a basis? Use a greedy algorithm, no? You use a greedy algorithm, right? What do? You take one vector. Suppose I give a bunch of vectors, and I say find a basis for this collection of the space spanned by these vectors. What do? You take the first vector, and then what is the next vector you take? It's a vector which is not in the span of all the ones you already took, right? Yeah? And then what's the next vector you take? The vector which is not in the span of the first two you picked, right? And you are guaranteed that it will give you a basis, no? Why are you guaranteed? Okay, that's because of linear algebra, right? And it so happens that there are many combinatorial structures where the same phenomena happens. That's why they're called matroids, because they came from matrices. Okay, so that's the reason why this thing works. So that's also the reason why spanning trees will work, and we'll see that in the MST lecture. Okay, so last example of interval scheduling. Okay, so I have now a different scenario where I have jobs which look like intervals, right? So they have a processing time, but they also have a starting time. So this job has a release time and a finish time. So it starts here and ends here. There are many such jobs, okay? So it could be, it can model things like, this class starts at this time, ends at that time, and so on. So this is a collection of intervals like this. And I want to find the largest number of intervals that don't overlap with each other. Okay? So I want to find these 4 intervals don't overlap with each other. Okay? So remember we saw the independent set problem where I have a graph and I have vertices and I put an edge between 2 vertices. I have edges, and independent set is a subset of the vertices which don't have any edges between them. This is the same problem except that I have my graph is induced by intervals now, right? I want to find the largest number of intervals which don't overlap with each other. Okay, what would be a greedy algorithm that you can use for this problem? If I ask you to design a greedy algorithm, what would you do? If you had to design a heuristic, what would you do? Right? You're in a Hack, Illinois or something, and you have 10 minutes to code this, or come up with an idea, right? What would be a natural heuristics for this? Maximize the number of nodes it's going through. What does that mean? So you have a graph, and then no, but how will you solve that problem is what I'm saying. No, so now you reduce it to a graph problem, but you know how to solve the graph problem, right? It turns out the graph problem is harder than the interval problem because it's obviously you can model things with graphs, right? It's an NP-hard problem, so you're reducing, which is fine. If you can solve the graph problem, you have solved it, right? You don't have to worry about it. But the graph problem is hard, so we have to see if, yeah. Okay, yeah, but how will you choose the first one? Earliest arrival time. So maybe you'll pick this guy. And so, the naive algorithm is pick any interval, kill everything that it overlaps with, right? Pick the next guy, right? And then kill everything that it overlaps with. It's not paying any attention to anything, right? But we want a little better. So he's saying earliest start time. Yeah? Why not, right? Okay. Is that a good algorithm? What if the earliest start time guy went all the way? It'll kill everybody, right? Okay, some other ideas? Yeah? Earliest stop time. So among these guys, what is the earliest stop time? This guy has the earliest stop time and the earliest, right? Okay. All right. Why? Yeah, so that's one intuition. Okay. What about the shortest one first? That seems intuitive, no? Yeah, this guy is not interfering with too many guys, so maybe that's good, no? I'm just thinking of that, Okay, so that's the problem greedy. So, okay. So, but the greedy algorithmic template is clear, right? You pick something. Once you pick it, you can't take it back, so you have to kill things that it interferes with, and then you pick another one according to some rule, and then keep going, right? So you can think of many things, right? Earliest start time is what he said, right? Yeah, you said, okay. In fact, it turns out that in this example, it gives you the right thing, okay? Okay, it gives the right answer, right? But as you saw, that the bad example is this, right? If you take this long one, you'll kill all this. It won't give you the optimal solution, right? Yeah. Okay. What about earliest, smallest processing time? This seems good for this example, right? Okay, you'll get all this right ones. What is a bad example? Okay. Okay, this is a bad example for the smallest interval first, right? Why? Because I can get these two, but if I take the smallest one, I can't take any of those. Yeah. Okay, here is a nice exercise if you are interested. What does this show? This shows that if I pick the smallest interval first, my solution can be half, no more, half of the actual optimum solution, right? This is the worst case. That is, smallest interval first will always get at least half of the optimum. Okay, if you want fun exercise, that's an exercise. Okay. Smallest interval first will always get half of the optimum. Okay? Okay. Fewest conflicts. What does fewest conflicts mean? That's a reasonable heuristic, right? If I have an interval which doesn't conflict with anything, I should take it, no? Yeah? Why not, right? Obviously, I'll always take any interval which doesn't conflict with anything. But so maybe say, if I have to take an interval, I should pick the one with the smallest number of conflicts because I will kill the least amount, right? Okay, is that a good heuristic? Well, this is okay. On this case, it is optimal. But here is a not so obvious counterexample to that. Okay, to the fewest conflicts. See, which one would the fewest conflicts pick? Sorry? It'll pick the middle one, right? Yeah? Okay, this is an interesting counterexample of the fewest conflicts first, because see, what would it pick? This guy has the smallest conflicts because it has conflicting with only 2, right? While all of them, because of this dummy guys, this guy conflicts with 3, this guy conflicts with 4, this guy conflicts with 4, this guy conflicts with 3, right? Yeah? So it will pick this. If you pick this, what will happen? You have to remove this, yeah? And you won't get the optimum solution, right? What is the optimum solution here? It is the top 4, right? Yeah? While if you pick the fewest conflicts, you will only get 2, right? Okay, so it doesn't give the optimum solution, okay? So as we said, we can also try the earliest finish time first. Okay? What is the earliest finish time? You pick the one with the smallest finish time. So this is the one, and you kill everything. What is the next one you'll pick? This one, right? So that, okay, then you kill that one. What is the next one you'll pick? That. Okay. Okay, this gives an optimum schedule. Okay. Earliest finish time gives the optimum schedule. Why do you believe that is true? I'm claiming it. Now our goal is to come up with a proof. Why is earliest finish time the optimum schedule? Do you believe that's true, or if you're not, I'm claiming it's true. What is the intuition, right? Okay, so thing is, as you can see in this problem, the optimum solution need not be unique, right? The optimum solution need not be unique. Yeah? There could be many different optimum solutions. So how can it be that this particular greedy algorithm's schedule is optimum? How do you argue that, right? Yeah? That's correct. So let's try to formalize that. But we have to argue that, remember, our objective is the number of intervals we chose, right? So let's can you rephrase what you said in a way that we can verify more formally? So what is a claim? Yeah. So that's yeah, right. So Yeah, but that's not quite. I'm trying to see how we'll formalize that into a proof, right? Okay, to formalize this into a proof, it is better to think of the algorithm a little differently. Let's maybe try to think of it a little recursively, this algorithm, if that will help us. Right? So, okay. So if you believe the greedy algorithm is optimal, what should be true? You committed to the first interval, right? You committed to the earliest first interval, right, in your set. There's no way you're going to change that decision, right? If you believe your algorithm is correct, what do you need to claim? That there must exist an optimal solution which includes this guy, right? Okay, if the greedy algorithm is optimal, any greedy algorithm you pick, how do you prove that? I mean, if you believe it is correct, it chose one interval first, right? Whatever interval it chose, right? It better be the case, because it's never going to pull it out. It better be the case that there must exist an optimum solution with that interval in it. Yeah, there could be many optimum solutions, but your job is to prove that there exists an optimum solution with the first interval that the algorithm chose. Because if there is no optimum solution with the first interval you chose, there is no way you're going to get an optimum algorithm, right? Yeah? Okay, let's rethink how we want to prove, right? The greedy algorithm, whichever greedy algorithm you chose, is going to pick an interval first, right? It's committed to that forever, right? It cannot take it out because it's a greedy algorithm, right? It chose that interval, it killed everything that it interferes with, and then it does whatever, right? If it already made a mistake in the first step, then there is no chance for it correcting itself, right? So you have to argue that its first step is correct, right? So one way to argue that is there exists an optimum solution which contains the earliest first interval. Okay, but the only thing we can prove that there exists one optimum solution, because the optimum solution need not be unique, right? So here is see, we cannot prove that the set that your algorithm chose is exactly an optimum set, because an optimum can have many, there is no unique optimum. So what you want to prove is that the size of your optimum solution is the same as the solution that your algorithm chose. Okay, but since it is a greedy algorithm, here is the key lemma which you should think about for any greedy algorithm. Let I1 be the first interval picked by the greedy algorithm. Then there exists an optimal solution that contains I1. This is the earliest first interval, right? We sorted the intervals as, say, the earliest I1, I2, IN are according to the finish time. That's your rule, right? So I'm going to claim that that gives an optimum schedule, right? How can I prove it gives an optimum schedule? By first claiming that there is an optimum solution which contains that the interval which finishes first. Why is that true? Why is your intuition true? Now I claim this. Can you prove this claim? Again, by an exchange argument. Pick an arbitrary optimal solution. If it contains I1, you're done, right? If it doesn't contain I1, how can you make it have I1? Can you add I1 to it? Right? If I can add I1 to the optimal solution, what happens? If adding I1 to the optimal solution makes it still feasible solution, you're happy, right? How can that be optimal solution? I added I1, which was not there in optimal solution, and now it's still feasible. That something is wrong with that optimal solution, right? So it means that I cannot add I1, right? Why can I not add I1 to the optimal solution? It overlaps with something in the optimal solution, right? Agreed? Okay, then I can't add I1, but how can I force I1 into that? I'm trying to prove that there exists an optimal solution which contains I1, right? So I want to add I1 and pull something out and make sure that I pull only one guy out, right? If I pull more than one guy out, I can't claim it's still optimum, right? So can there be more than one interval in the optimal solution that overlaps with I1? Why not? No. Remember, okay. So let O be an arbitrary optimum solution. If I1 belongs to optimum O, we are done, right? Because that's what we're trying to prove. But if I1 is not in O, then I claim that exactly one interval J1 in the optimum solution which overlaps with I1. If I prove that claim, I can add I1, remove J1, and I'll still get the same number of intervals in the optimum solution, but then the new optimum solution has I1, right? Yeah? Yeah, how can I argue that, the optimum solution has at most one guy that overlaps with the interval I1? Suppose not, right? Suppose there are two intervals in the optimum solution that overlap with I1. Okay? Well, how can they overlap with I1? Any interval that overlaps with I1 has the property that it overlaps at the finish time of I1. Why? Because I1 is the interval with the smallest finish time, right? If any interval overlaps with I1, it has to overlap with I1 at its finish time, right? If there are two intervals in optimum which overlap with I1, they both must overlap with I1 at the finish time of I1, but then they would overlap with each other and say they cannot be together in the optimum solution. Okay? So there can be at most one interval in the optimum solution which overlaps with I1. So what can I do? I can put I1 in the optimum solution, pull that guy out. Has the size of the solution changed? No, right? Because I exchanged one guy for I1, right? So now what does the new optimum solution look like? Does it have I1? Okay. So what did we prove? We proved that there exists an optimum solution which contains the interval with the earliest finish time. Yeah? Okay, then we are done, right? Because what is the earliest finish time algorithm? It's a recursive algorithm. You can think of it as a greedy algorithm or a recursive algorithm. It's better to think of it as a recursive algorithm, right? What does it do? It includes the interval with the earliest finish time, right? Then kills everything which overlaps with I1 and recurses on the remaining thing. Is it the same algorithm? Yeah? It's the same algorithm, right? It's a greedy algorithm, but I'm thinking of it recursively. But if you think of it recursively, with this claim you're done, right? You have shown that there is an optimum solution which contains I1. So I will add I1 and I'll recurse on remove everything which interferes with I1. Optimum also has to remove everything which overlaps with I1, and then I recurse. Okay? Is that clear? Yeah? So the key thing is what? When we do a greedy algorithm and you include your first interval, it better be right? If you don't make the first decision correctly, then you are host already, right? So the key to understanding a greedy algorithm's performance is that why is the first step the right one, right? Okay. In this case, if you cannot argue that your first interval is in an optimal solution, you have no proof at all, right? You have to develop an intuition of why you have your first step is correct. In this case, why is there an optimal solution with your first interval? So then, because the optimal solutions do not be unique, you have to see whether you can create an optimal solution which contains the first step, the interval you took. Okay? If you cannot do that, then that means you have to suspect that your algorithm is not correct. All right? So that's the idea. Okay? So that's another way of doing that. Okay, this is actually an interesting data structure question. How fast can you implement this algorithm? Earliest finish time first. Okay, no, I won't show you the solution. Okay, so I give you intervals. How are the intervals given? Left endpoint, right endpoint. How fast can you implement this algorithm? I give you a bunch of intervals, right? Each interval is given by 2 endpoints, 2 numbers, right? How fast can you implement the earliest finish time algorithm? What would you do? You'll sort, okay? Yeah? And then what? You can find the I1 for easily, right? But what about the next guy? What do you need to do? Yeah, but how can you do that efficiently? Okay, is the problem clear? I want you to implement the algorithm fast. Let's not worry about correctness. Yeah? Yeah, right. You sort all of them by their finish time, right? But the next guy, when should you kill it? If its start time is before the finish time of the previous guy, right? Otherwise, you take it, and so on. Okay, so it's actually, if you sort, you can do it in analog n time. Okay, okay. What about the problem where now I give you these intervals, but each interval has a weight associated with it. Okay, this guy has weight 100, this guy has weight 1, this guy has weight 2. How will you solve that? Greedy algorithms don't work when the intervals have weights. Okay, but you can solve it by dynamic programming. Okay. Okay, so in fact, you should solve this problem by dynamic programming and not a greedy algorithm. Okay, the only reason I teach this in the thing is this way is because it's a simple greedy algorithm. It works. Okay, because the only reason it works is because the intervals have the same weight. If they have different weight, no greedy algorithm works. You have to do dynamic programming. Okay, but I want to do something which is even nicer for fun. No, that's a different scheduling problem. Every problem is different. You can't compare the two, right? No, that one, yeah, greedy algorithm still work, but not on this one. Okay, so I want to do one last thing. Instead of doing dynamic programming, here is a reduction to graphs. Okay, because I like graphs, right? And here is a simple, cute reduction to graphs. So here is a graph, right? Put a vertex here. Okay, so what is the graph I can create out of this? A DAG. Can I create a graph out of this? I can do anything I want. Yeah, sure. So I'll create a graph like this. Okay. I want to get non-overlapping intervals, no? So I'm going to create a graph visually like this. So, where should I jump from here? So I add edges from only the intervals which don't overlap with it, okay? Okay, so I mean, I add edges to here, edges to here, edges to here, edges to here. I mean, okay, so for every endpoint, I add an edge to another endpoint where there is no overlap, okay? So now what do I get? Do I get a DAG? Yeah? I'll get a DAG because all the edges are oriented from left to right, okay? Now I find the longest path in this DAG and it will give you the right answer, okay? Okay? No DP, even weights will be handled. Implicitly it is doing what? Dynamic programming, okay? But you don't even have to know dynamic programming. If you know graph algorithms, you can reduce it to a graph problem, right? Longest path in a DAG, okay? In a DAG you can, because you can convert the weights into negations and you can find longest. There are no cycles because you can find longest paths in DAGs are possible because you can negate and find shortest path and there are no negative length cycles, so you can find longest paths in DAG. Right? So that's why it's important that it's a DAG here, okay? But what it is doing is dynamic programming, okay? So there are many ways of solving this problem. All I'm trying to say is that it's good to think about graphs too, all right? A lot of the DP problems can be solved by graphs, by DAGs, and there's a nice connection between DAGs and dynamic programming. Unfortunately, I didn't have time to go over it in lecture, but it's in the notes, right? I put up some notes on connection between, one of the sections is on the connection between dynamic programming and DAGs. Okay, read that because it'll give you some ideas on solving problems which are kind of cute, and you'll see why. See, isn't this nice that you can solve it by a DAG problem even though it doesn't appear that, right? But it's really very simple connection to DP here. Okay, all right. So greedy algorithms, the main thing you need to to worry about is why your algorithm is correct. You have to be even more cautious about greedy algorithms than all the other techniques, because as you saw, it is not easy to see why something is correct, right? So be very careful about greedy algorithms. Don't try to use them if possible, okay? It's important to cover them, but it's not the first thing you should try.